Good afternoon. It is truly my distinct pleasure to welcome you all to the 2018 Makhlouf Haddadin lecture. We are very thrilled and honored to host Nobel Laureate Sir Fraser Stoddart to deliver the 2018 Makhlouf Haddadin lecture. Professor Makhlouf Haddadin is the longest serving faculty member at AUB. He is a distinguished eminent scholar in organic chemistry with extraordinary contributions to the chemistry department, AUB, and the community at large. On February 8, 2011, the Makhlouf Haddadin Endowment was initiated. And on March 18, 2015, the Makhlouf Haddadin Lectureship was launched. Sir Fraser is the 10th speaker of the Makhlouf Haddadin Lectureship. Sir Fraser was born in Edinburgh, Scotland in 1942. He obtained all his degrees from Edinburgh University and spent time at Queen's University, Imperial Chemical Industries, and the universities of Sheffield and Birmingham in the UK before moving to the US in 1997. Presently, Sir Fraser is a Board of Trustees Professor of Chemistry at Northwestern University, having previously been the Sol Winstein Professor of Chemistry at UCLA. He was honored by Her Majesty Queen Elizabeth II in a Knight Bachelor in her 2007 New Year's Honors List for his services to chemistry and molecular nanotechnology. Sir Fraser received the 2016 Nobel Prize in Chemistry along with Professor Ben Feringa and Professor Jean-Pierre Sauvage for the design and synthesis of molecular machines. Sir Fraser's talk is entitled The Rise and Promise of Artificial Molecular Machines Based on the Mechanical Bond. Before I hand the floor to Sir Fraser to deliver his seminar, I invite Professor Haddadin and Sir Fraser to join me here. Professor Haddadin will be handing a small token of appreciation to our distinguished guests. And we will also hand a copy of the seminar announcement to Sir Fraser.
This is quite large. Yes.
It's heavy.
And heavy, yes.
I know, I tried it.
Okay.
Now we put it in the right place.
Oh, gosh.
Thank you.
I need a donkey. Yeah, yeah. Wow. My goodness. Amazing.
Also, Dr. Haddadin, this is a copy of your seminar.
Wow.
Thank you.
Thank you.
Bilal.
Sir Fraser, the floor is yours.
Oh, yeah. Well, good afternoon, everybody, and thank you very much for coming to this event. It's a great pleasure to have been invited to give this lecture marking the big contributions that Professor Haddadin has made to chemistry and I guess many other exploits here at this university. I've been lucky to be associated with him for the past 24 hours, and you're just a wonderful man. Thank you.
The pleasure is mine.
Oh. And the pleasure is mine. All right, so thanks very much, Bilal, for your very short thank you introduction. So I'm going to talk about molecular machines ultimately, but before I get there, we're going to look at engines through the ages, and we'll look at steam, electric, internal combustion, diesel, jet, rocket, and then we'll take a little time out to look at the biological motors that are so important to all of us before we visit these new artificial molecular machines. And who knows, there might be more to come after the nanomotors that I've been associated with, along with Jean-Pierre Sauvage and Ben Ferenga. So I should point out that central to all this is the wheel. And the wheel is one of the 6 simple machines, the other ones being, if I can remember them, the lever, the pulley, the screw, the wedge, and something called the inclined plane. This is number 6. And this particular one is over 4,000 years old, and it comes from probably not too far away from here, what I guess I learned was Mesopotamia when I was a little boy. Anyway, we'll move on up to a period of the 1700s when the steam engine came into being, and this 1765 is a steam engine courtesy of Scotsman James Watt. And here you see one from the United States, from the state of Pennsylvania, that was used at this time to drill for oil. They soon found their way, these engines, into wheels that were moving contraptions that we came to know as trains. And this is one of the most famous ones in the Science Museum in London. This is Stephenson's rocket. And going fast forward from 1820, whatever it was, to 1923, here is the then, at that particular time, a variety of the Flying Scotsman that cut the journey down between Edinburgh and London to 6 hours. And then back in the United States, on the West Coast, this particular steam engine and the train behind it plies through Oregon, showing tourists the wonderful landscape there. Now, let's go to electric engines. And this 1821 contraption here is one of the early demonstrations by Michael Faraday that you can convert chemical energy into mechanical energy. And let me restate that. You can convert electricity into mechanical energy. And here is the first electric motor, courtesy of a Hungarian, János Zsedlik. And apparently it still operates in a museum, of course, to this day. Here is an electric motor that was a gift from James Joule to Lord Kelvin in 1842. And then we're all familiar with the contraptions that we use to dry our hair and to move ourselves along our highways and byways. Here's a Tesla. And for those of you that go to China, you have this remarkable experience of being hurled along at, 400 kilometers an hour.
The Beijing to Shanghai high-speed train has even clocked in speeds up to 400 kilometers an hour. That's about 300 miles an hour.
Quite amazing. And more or less 60 cities the size of New York in China have now been joined up by these very high-speed trains. Internal combustion engines that are so important to our cars was von Langen, a German, in 1863. This was the patent that he produced for the first gas or petrol engine. A year later it was in production, and going fast forward, by 1908 the Ford T2 had graced the marketplace, and for the next 20 odd years to 1927, there were 17.5 million of those sold, mainly in America. And then to the present day, this is my recently purchased Toyota Corolla, and it has a very privileged home on the Northwestern campus, because up here you can see there is a parking spot that is reserved for my Corolla. And if I bought another car, it could also share this particular spot, but I'm not going to do that. Okay, diesel engines. When I put this talk together, it was on the 8th of May, I spoke first about engines through the 80s in the Science Museum in London, in front of, we say, the great and good of the city and beyond, including the Princess Royal. I learned for the first time that diesel is derived from a person, Rudolf Diesel, a German. And this was his first diesel engine. Here is one of almost the present age that is making its way into presumably a cargo ship of some kind. Jet engines, one immediately thinks of Sir Frank Whittle, who during this period really dominated the scene in the design of these engines. And if we look here, you see a Lockheed Martin F-22 fighter taking off. While the Qantas Boeing 787 comes into land at Heathrow. This was in March. It had flown 9,000 miles in 17 hours. And that is a record in terms of distance. Now, here is something to make you think. And, you know, this is a revolution in my lifetime. Of course, I don't go back to 1905, to the time of the Wright brothers, but really flight has only been available to the likes of you and me for the last, I would say, 50, 60 years. But now, there are 12,000 of these contraptions up there in the air at any one time. You put 200 in each of them, and there's 2.5 million people, not on planet Earth, on the ground here, but they're up in the sky. It's more than half the population of Lebanon. Now think of that. Right, rocket engines. Well, this is not such a nice beginning. When I lectured in London, one of those was only a meter away from me. This is a V2 rocket that was brought onto the scene by the German war machine in the final days of World War II. And of course, a lot of people lost their lives in London, Antwerp, and Liège, and places like that. In more recent times, but still now history, Apollo 11 was the home of Bud Aldrin and also Neil Armstrong and their journey to the moon. And then this is a personal footnote here. Helen Sharman was a chemistry student at the University of Sheffield when I was there, and she and I wouldn't have predicted that at that time, because I was her organic chemistry tutor, she turned out to be Britain's first astronaut. And so there you see Helen and the fact that we are now connected on Twitter today. Here is SpaceX's rockets actually landing. So they can not only take off, but they can now land. Biological motors. Well, this is the archetypical myosin and actin at work, which is what allows us to have many of our muscular movements. And down here is the source of the chemical energy that is produced when adenosine triphosphate, ADP, joins up with phosphate to give us adenosine triphosphate. And this rotary motor is housed in the walls of our mitochondria. And of course, the ATP is fed up here to drive our muscles. And all we normal adults are actually producing somewhere in the region of 40 kilograms, which is half our body weight of ATP every day. Of course, as soon as we make it, we use it. If you're involved in physical exercise, such as Serena Williams, you will probably produce about a ton of ATP as a result of that exercise. And so, well, he's a Scot, so I had to show you him. Andy Murray. All right, so let's now segue into the artificial molecular machines by talking about mechanical bonds. But let me first of all point out that bond, that word, means different things to different people. We don't, as chemists, those of us who are in the room, have a monopoly on the word. Financiers use it, biologists use it, social scientists use it, anthropologists use it, and it also pervades nature and art and architecture. And then in a more light-hearted vein, of course, if you go to the cinema, you will come in contact with James Bond. And Sean Connery, I was twice accosted in the streets in Los Angeles. Are you Sean Connery? No. All right, so going back to molecules is what my story is about. In order to get to these mechanically interlocked entities called rataxanes and catenanes, we have to visit, first of all, the complex, and we call this a pseudorataxane. And the mechanical bonds are made at the interface between what Jean-Marie Lane calls chemistry beyond the molecule, and getting back into the molecular world, into what I call mechanically interlocked molecules, or MIMS. And what operates here is molecular recognition, self-assembly, and template-directed synthesis. So these mechanically interlocked molecules, just to define them again, the rataxane at its simplest level is a dumbbell with one ring, and is derived from the Latin that you see there. And two rings also end up giving you a 2-catenane, again derived from the Latin. So with that introduction, we're going to go on and establish the molecular recognition that led to being able to make molecular shuttles and switches and ultimately machines. And we will be doing this courtesy of templation. And having made them, I will talk about molecular shuttles and switches. Then I'll introduce the concept of energy ratchets, radical templation, molecular pumps, and in a fundamental sense, doing chemistry away from equilibrium. And at the end, I'll make some philosophical comments. So establishing molecular recognition. Well, if you were at my talk this morning, you would have heard that at some point in my period at Sheffield, I went to Imperial Chemical Industries corporate laboratory. And while I was there, I discovered this very simple, sometimes called methyl viologen, and it has a great history as a redox agent in many, many different parts of chemistry and biology. It was being marketed as a wipeout weed killer at that time by ICI, called paraquat. And we began to realize that this pi electron deficient system would probably interact with pi electron rich ones like dimethoxynaphthalene. And so if I define some icons, molecular recognition is off when the key is out the lock and on when it is in the lock. Templation will be indicated on my slides by the template here that chemists should be familiar with. We'll come to radical recognition subsequently, and also the use of heat in order to drive shuttles and switches and machines. And then redox control, which could be either chemical, electrochemical, or even photochemical. And then we'll see some ratios from time to time, and we'll often use some chemicals as simple as acids and bases. And so here is a movie that shows where we were about 1985 in terms of putting blue, the deficient thing, inside a red macrocycle. Having achieved that objective, we switched the recognition round and put red into blue. And as we were doing this, we had to find a new and efficient way of making what became known as our little blue box. And so this was made using this template, which had to be removed after the reaction in order to give us the free blue box. All right, so that's the recognition. Now we're going to use it to make catenanes and rataxanes. And so this 1989 paper was a defining moment in, I guess, my research career, because it was a very simple experiment. It was taking this entity here, a dication, and reacting it with this dibromide. The dication does not recognize this template at all. There's no interaction between them until a covalent bond is formed. And when that covalent bond, nitrogen to carbon, is formed, we switch on a bipyridinium site. It's the same as in paraquat. And so it's not unreasonable to assume that it will find its way into the middle of this ring, which is what happens. And at this point, we've switched on, as a result of making a covalent bond, all this non-covalent bonding, which is, historically, it turned out to be mainly hydrogen bonding with some donor-acceptor interactions and some weak CH-pi interactions. The second nitrogen-carbon bond is formed virtually spontaneously, switching on more of these interactions, and we've got the mechanical bond now. So we've gone from the supramolecular world in this step here back into the molecular world. And what's really exciting about this discovery is the fact that the non-covalent bonds live on in the molecule afterwards. And so apart from it being a 70% yield and this X-ray crystal structure, which shows that the acceptor, donor from, if you like, the northeast down to the southwest here are at 3.5 angstroms distance from each other. There's a lot of DNA-like character in this artificial catenane, and there's also a bit of proteinaceous type interactions with CH-pi's here and behind the scene there. So this movie recaptures the making of the catenane. This ring comes on. It speaks to the recognition unit here, and then it closes up. And you have this 2-catenane that is, to all intents and purposes, no bigger than 1 cubic nanometer. And because of the living on of these interactions, you can see 3 different processes using dynamic NMR spectroscopy. There's this very fast one that's happening about 2 million times a second. We call it rocking. This one I call pirouetting. It's happening just about 2,000 times a second. And there's no control on the direction here. It can be clockwise, it can be anti-clockwise. And then there's the third one, which rips all the non-covalent bonding interactions apart, and so is the slowest. It's happening about 30 times a second, and again, it could be clockwise or anti-clockwise. So having made our first donor-acceptor catenane, it was fairly obvious that we should make a rataxane of the same kind. And so the template now is this dumbbell with these 2 recognition sites. The chemistry is the same as before, more or less, and the same interactions come into play. The yield is lower because although I draw this like this, it is not as pre-organized a template as is a crown ether ring. So we're at 32% now. And the movie shows, again, I hope quite elegantly, how the pieces probably come together during the templation here, and then the formation of that last carbon-nitrogen bond, so that you actually clip a ring onto what is a dumbbell. So this took us to the next realization that was really very exciting at the time, in 91, that this blue box is jumping back and forth in a degenerate manner between these two hydroquinone rings roughly 2,000 times a second. And we're talking about something well over a nanometer, probably a nanometer and a half jump between these two. Now, when we look at it with the movie, it allows me to remind you that, again, by dynamic NMR, we can work out how fast this ring is going back and forth. It's about 2,000 times a second. The barrier it's got to get over is round about 13 kilocalories per mole. And it came time to publish it in the Journal of the American Chemical Society, and these were the last 4 in this communication. And the then editor, I won't mention his name, leant very, very hard upon me to remove all these words. They were hype. They were hype. And I stuck to my guns, and there's some times in life when you've got to believe in yourself and you decide, no, I'm not going to give in to an editor. And I just read out this second sentence. Insofar as it becomes possible to control the movement of one molecular component with respect to the other in a two-rotaxane, the technology for building molecular machines will emerge. So this was the first time I actually mentioned molecular machines. The next thing was to desymmetrize this shuttle so that we had this green unit, which is benzidine. The red unit is now a biphenol. And we did predict that the ring was going to spend more of its time on the green, 84% of the time, than on the red. So it wasn't quite a perfect, as it were, potential switch, but is well on the way to that. And so we explored its switchability. And before we go there, I'll just use the movie here to show that it's spending most of its time here and about a quarter of its time up there on the red one. But what we can do here is we can protonate these nitrogens and use physics, Coulomb's law, to say this ring will have to move to the red station. And it does to an extent of 100%. Until you add base, remove the protons, and it will go back 84% of the time onto the green. And so, again, this movie will illustrate what I'm talking about. So now we have a molecular shuttle, a molecular switch, but we do not have a molecular machine, if we are being very precise about how you define a motor or machine. If I just take the switch, we switch it on, we switch it off. No work is done. So if we're going to go forward and make machines, we have to climb higher mountains. And this was a grand challenge, and it has been for most of this particular century. And here you see a macroscopic machine. This is a Dutch artist rendering of a wooden sculpture with sails here that on a windy day will walk its way across a flat beach in the Netherlands, in Holland. Whoops. And down here you have another of these molecular motors that is replete in our body, again, of the walking type. And the physics is very different between how this behavior takes place. It's all concerned with inertia, momentum, friction, and gravity, whereas these things are not counting down at the micromolar level. Down here it's thermal fluctuations and the fact that we have Brownian motion, things are constantly on the move, and it is the viscous forces of the rest of the cell that will be at play and hindering the movement of one component here with respect to the other. And so, just to further make this point, if it was a mechanical approach that we were looking at, we could start off down here in this valley and we want to get up there. This could be a car or a bicycle. We just make our way across into this valley here and then across the mountain into this one. That's not the way that biology works or our artificial molecular machines work. It's all about juggling about with energy levels. And so what we've got to do here is raise the energy of what I will now call a collection of molecules, so that at the same time we maybe reduce the transition state here, put them into a well that they sit in temporarily, and then we do further switching by raising this well, so that over the mountain here that we take the top off, and eventually we end up with the molecules on the right hand side. So it's all a bit of a juggling act. And so this has been called a flashing energy ratchet, and this is an example we described back in 2013, where this is not quite a dumbbell. This ring is able to come on from the green side and depart from the blue side, this one being neutral and this one being charged. And this happens because under just the addition of these two, the recognition of the ring towards the red unit will be enough to drive it on to the dumbbell. And then if we carry out a reduction, we switch off the recognition between the red and what was the blue unit. This is now a bis radical dication. It no longer wants to stay on this energy minimum. It's now been raised, as I'll show you in a minute, and it prefers to leave by the right-hand side. We've reduced the charge from overall 4 plus 1, 5, to 2 plus 1, 3, and we also, I think, changed the shape of the macrocycle in so doing. And so, linking it back to this very simple energy profile, what you see here is the blue box making its way over the easier barrier of the two, the green one, the neutral one, and then the reduction raising up the well and pushing them up over the charged end. So that energy ratchet can be illustrated again with these movies that you're now familiar with. Comes on, and then there's this reduction, switches off molecular recognition, reduces the coulombic charge, and it leaves by the right-hand side. But with this energy ratchet, again, we've still not done any work. We take a ring out of solution, and we put it back into solution. No work is done. But we are making progress. And we were able to make progress because of a young boy from the Lebanon. His name is Ali Trabolsi, and he was schooled in this city at the Lebanese University, not this one, but the other one, or one of the other ones. And after he got his bachelor's degree, he went to Strasbourg, and he worked there with, you have to help me, Ali. Anne-Marie Albrecht, yes, a physical chemist. So I want you to note, a physical chemist. And then he came from Strasbourg in the January of 2007 to UCLA and spent 9 months before moving with me to Northwestern and then spending the best part of another 2 years. And he's now a professor at the fairly near New York University at Abu Dhabi, and is doing terrific things. And what did he come up with? Well, a little bit of history. he noted that if you just take methyl viologen, it undergoes, over here, polymerization. This is a process whereby the radical cations are formed and they come together into stacks, and in particular to form this, as it were, dimer. And this is the evidence in terms of physical parameters, both in acetonitrile and water. And there were earlier forays into this, because there are never any firsts in science. So here's an example where a cucurbituril has been used to trap a particular example of this dimer. But this was the big discovery that Ali Trabulsi brought to the lab. The fact that he could take our little blue box and paraquat and kill free of the positive charges by putting free electrons in. And it took 25 years for this to happen. And he wasn't a synthetic chemist. I remember he created his own, what we call glove box, his own inert atmosphere in a kind of haphazard sort of way. But it worked. And he was able to show very quickly that you get complexation. And this complexation is very high. It's higher than we get between donors and acceptors. And so nowadays we do it with zinc dust and nitrogen and acetonitrile, and you make this complex. And these again are the parameters, a stability constant of over 5, where it is enthalpically driven against a negative change in the entropy. And in collaboration with with Albert Fahrenbach, a graduate student at the time, they pushed on, and by 2012 we had a crystal structure, and came to realize that the structure was such that the one-to-one complexes were in an infinite stack. And so the last slide here paying tribute to Ali is one where he did this very elegant work that showed radically enhanced molecular switches, where effectively here he has a tetrathiophylvaline unit, which is a great lover of the blue box, and a bipyridinium unit, and also a dioxynaphthalene unit. And he could make the ring move between these three simply by, on oxidation of the TTF, the ring leaves all these positively charged entities and goes to the neutral dioxynaphthalene. This is charge transfer, it's donor-acceptor interactions. And then if he does a free electron reduction, it will end up on the bipyridinium unit, courtesy of his discovery of 2010. And if he then has the state 0 here, then it will be back on the TTF unit. And this could be followed by absorption spectroscopy. Now, the amazing thing here is that this boy from the Lebanon has established what I would call a radical school at Northwestern. And these 13 sort of major players are only the tip of the iceberg. There'll be another 30 or 40 who've dabbled in a radical chemistry. But if I go around and say, professor at the University of New South Wales, professor at the University of Washington, Honeywell in industry, a professor at Macalester College in the state of help. No, I should get this. It's where the two cities are. Minneapolis, yeah, is one of them. What's the state? Minnesota, thank you. Carson Bruns, University of Colorado. Marco Frassoni, University of Pavia. Haoli University, Zhejiang University, Chu-Yung-Chen, Sishin University, Paul McGonigal, Durham University. Yuping is a postdoc at MIT at the moment, and he is looking for an academic position this year. Christian Pizzato has just won a big fellowship to return to Europe. He's Italian, he's going to Switzerland, to Lausanne, and Mark Lubke is at Rutgers University. Amazing, totally.
Now everybody want to go work with you.
Yeah, Ali, stand up. Well, you're up there with the very best of 550 years. If he can do it, any of you young people in the audience can do it, all right? All right, so he introduced these radicals, and what we could do was redefine our energy ratchet such that we could turn the dumbbell through 180 degrees and bring the ring on from the charged side and push it off from the neutral side. And this led to the design of a molecular pump where the ring is going to come on from the left here over this charged unit. It's going to be brought on by the radical chemistry, and then we're going to oxidize, and it's going to then be moved to the right here over the steric barrier, or speed bump as we sometimes call it, and we're not going to let it escape. And because we're not going to let it escape, I don't know if that's going to work. We're actually now going to be able to do some work. And so you see these movies, and I do the steps here of the ring coming on, and the speed bump here is coming into being when we do the oxidation. The ring sits here, as you'll see, for an hour and a half at about 40 degrees before it goes over there. So we need to use heat to get it to go over. That's the symbol for heat. And we can repeat the process, and we can put two rings on. And so we can make both a 2 and a 3 rotaxane. All right, so now we're doing chemistry away from equilibrium. So we've got a situation where here is the chemical constitution of the pump, and I just show you briefly some proton NMR spectra. Here are signals that are key to the whole process of the pump. And you'll notice that on reduction and oxidation, so this is a treatment with zinc dust followed by oxidation with nitrosyl hexafluorophosphate, the spectrum changes quite remarkably, and we begin to see the beginning of high field signals that indicate eventually that the ring is on this collecting polymethylene chain. And it takes roughly an hour and a half at 42 degrees for this to make its way ring all the way over. Here we have a repeat of the process for getting the second one on. All right. Okay, so let's play it through with the movie so that, oh, there's another one back. They like me. Speed bump and the collecting chain. And notice in the reduction, this would want to come back, but speed bump plays a secondary role of not allowing it to come back. And so there we have 2 of them on there. So to summarize, we're doing chemistry away from equilibrium. The first ring is coming on to the level of 90% yield, and the second one to 85%. So overall, the free rotaxane is a 77% yield. All right. The main thing about this slide is the almost within experimental error, exactly the same barriers to get the ring to go over the speed bump. So this tells us that the presence of this ring here doesn't inhibit another one coming over, which is good news. And so going on, and this is what we're doing now, we're pumping more and more rings on, and what I show here through this redox process is that the energy level is rising as we bring on a third and even a fourth ring, and then we run out of room on this particular movie. So now each cycle traps one ring in a high energy state. Some of the energy input is trapped, work is done. So now we have actually made an artificial molecular machine. What good could this be? Well, it can lead to so-called entropically dominated polyrotaxanes. And before we go to those, I just want to point out that in more recent times, this was just published last year, we have speeded up the whole process. So now you're looking at spectra that are being run at room temperature, and through the same kind of routine, it's taking the same length of time. But if we extrapolate up to 40, 42 degrees, this will be occurring in certainly minutes, if not seconds. All right, so we can also control the threading of multiple rings onto polymers by putting pumps at each end of something like a polystyrene or a polyethylene glycol chain, and that we're working on at the moment. But the one I'm going to show you is one where synthetically this oligomer with, 18 methylene groups with 2 ammonium centers parked in the middle there, has been used as the collecting area. And it'll be very, very high energy because the rings coming on with their positive charge are going to be put on a positively charged link. And this can be done now electrochemically with this apparatus here, so that you have the reduction phase, you have some time for the ring to come on over the neutral end, and then after that you do an oxidation and send it over the speed bump. And here's the very nice NMR spectrum of the free rotaxane that Christian Pizzato obtained, and he repeated it and got the 5-rotaxane here with, again, a beautiful NMR spectrum. Okay, so now we have set the scene to make these entropically dominated polyrotaxanes. And here is just finally the movie to try and capture what I've been telling you. These could be useful in new materials, in making polymers where you can get scratch resistance and things like that because of the movability of the rings on the polymer chain. All right, so I think we've now reached the stage where I'm going to have a little bit of a rest myself for about 4 minutes, and if it works, we're going to have some recall of what I've been telling you. And so pressed into just 4 minutes and I think 20 seconds is 35 years worth of research. Hello.
Dance all night long.
Yeah. Bye-bye.
Oh, you know the lyrics
1,
too?
2, 3. 1, 2, 3.
Rien de rien.
You know the French better than
Oh,
me.
sure.
Sure. Yeah.
You know Scottish better than me. You have to sing. You have to sing.
No, you sing.
Tout ça n'est bien
Bye.
égal. Non.
This is fun, isn't it?
Yeah. Everyone's looking.
You ever danced at a lecture before?
No,
No?
first time. There's a first time for everything, right?
Yeah, oh, yeah, yeah.
Have you ever danced?
Yeah,
Oh, you without
Yes.
without your partner, which is me.
sorry?
Without a partner, like
No,
me.
no, no. I've had partners in other places.
Not me.
Yeah, yeah.
No, I'm sad now. Thank you a lot. See you tonight. We're gonna dance.
Yeah,
at
yeah.
Bilal.
Thank you, Sarah. All right, so let me just summarize by saying, really, the molecular shuttle was the big part of the movement towards the machine. 91, the switch in 94, and the machine I talked about today in 2015. Quite coincidentally, on the 7th of November, this book, The Nature of the Mechanical Bond from Molecules to Machines, was published between hearing about receipt of the Nobel Prize on the 5th of October and going to Stockholm to receive it on the 10th of December. And it's a 6-chapter book, I think fairly light introduction. It could be for the layperson. A couple of chapters on making mechanical bonds, under kinetic control and under thermodynamic control, and then topology and architecture, and then very importantly stereochemistry. I come back to that in a second. And finally, of course, molecular switches and machines. And most of the heavy lifting was done by this man that I've introduced you to already, Carsten Bruns. Now, this is where people ask, what are they good for? Before we start going to nanobots and things like that, which we can visit in a minute, they're going to revolutionize chemistry. So I have just listed here what I think are 36 different terms that either we had to invent or we had to use from the recent literature on the mechanical bond. So stereochemistry is undergoing a revolution courtesy of the mechanical bond. And I'm not talking about chiral or stereogenic centers. I'm talking about planes of chirality and axes of chirality. The book is being translated into Chinese. The lead person is Andrew Su, and these are two of his research students that are helping him in this mammoth task. And here is where I want to get a big message across. Chemistry is not an old science. Chemistry can be put up as the newest of the sciences because we're always able to reinvent ourselves. Chemistry creates its own object. Marcel and Berthelot in French in 1860. Chemistry is in the same court as, or chemists can be in the same court as painters, as sculptors, as novelists, as composers. You have every opportunity to create your own world just using atoms to make molecules and so forth. And so the mechanical bond really only came into being, well, in 1983, Sauvage made his big foray into the field. We came, as you know, in 89, 91, and see how it has taken off. And of course, citations follow it. And where is it happening in the world? Well, in the US, the UK, other parts of Europe, it's creeping into the Middle East here. That Japan is, of course, big in the game, and China is catching up quickly. And I must pay tribute, of course, to my fellow laureates. Here you have Jean-Pierre Sauvage and there Ben Ferenga. There are other people, including the Italian group of Vincenzo Balzani or Roberto Credi. My former student, David Lee, at University of Manchester. Physicist Dina Stumian at the University of Maine, who is an intellectual driving force for the chemistry that we and many others are doing. Joseph Mikkel in Colorado, often in Prague now. Steve Loeb in Windsor in Canada. Edie Sevic in Australia, the Australian National University. So Mexican Miguel Garcia Garibay. Polish boy Rafał Klein at the Weizmann Institute. New Zealander Amor Flood at Indiana University. Armenian Ivan Ebrahimian at Dartmouth. And Frenchman Nicolas Giusepponi in Strasbourg. And, you know, I didn't mention so much the nationalities on that side, but the diversity is what drives the field forward. And here is one of Sauvage's well-known molecular muscles in action in an abstract kind of manner. And then here's Ben Ferenga. He didn't work on mechanically interlocked molecules, but on this very elegant rotation about carbon-carbon double bonds promoted by a sequence of light and heat and the appropriate substituents on the rings attached to these aromatic units. All right, so if we look at the development of these engines that I started off with, the blue indicates that there wasn't much on the horizon. Green indicates a period of development of the engines, and the maroon would indicate the fact that they're fairly well developed and are being used in an application sense. Of course, in the biological world, they've been used in an application sense from time immemorial, and it's just in recent times that we've begun to appreciate just how they work and how important they are. But the artificial molecular machines, well, we're still largely in the field of fundamental discovery and invention, but I can see it taking off over the next few decades to give us many applications. And Just to put it in context, here is the Hungarian that described for the first time, invented this electric motor. Notice the gap here of 50 years almost, or more, to get to a working fan. Here is an early food mixer, believe it or not. Here is a hairdryer from the 1920s and a more up-to-date food mixer. But sometimes, and I urge all the young people and the not-so-young people to be on Twitter, you get some encouragement from people that just come out with statements like, your research on molecular machines has strengthened the development of nanobots. Also, it will help in developing swarm intelligence in nanorobots to the extent they control the number of bots. Thank you for your contribution. So, a little bit of philosophy to end on, and this was mentioned by the president of the university in his speech earlier today. The statement of Vannevar Bush, who was a scientific advisor to Franklin D. Roosevelt immediately at the end of World War II. Scientific progress on a broad front results from the free play of free intellects, working on subjects of their own choice in the manner dictated by their curiosity for exploration of the unknown. Helmut Schwartz thinks along the same lines in an article published in Nature Reviews Chemistry on the usefulness of useless knowledge. Fundamental research gives young people, like many of you in the audience, the opportunity to head for new shores. In order to master the future together, the enthusiasm of young people is the most secure currency we have, the Lebanon has. The principle of trusting people, rather than trusting a monitoring system based on distrust has proved its worth. The principle of funding people, rather than projects has withstood the test of time. And I will, I think, talk a little bit more about that maybe tomorrow. And not only do scientists see it this way. Here is Eleanor Caton, New Zealander, gets the Man Booker Prize for her novel The Luminaries. And when she goes to Wellington University to get her doctorate, here is what she had to say. The purpose of a university is not to replicate, but to enlarge. Not to simplify, but to understand. Not to reflect or serve the world in which we live, but to enrich it through the creation and exploration of an infinity of other possible worlds. So I leave you with these philosophical comments in the hope that they raise your spirits and try to get your governments and funding masters to think in terms of blue sky research, not just in the fixing of this and that in a project-oriented way. So we've been very lucky to be well-funded in all these different countries and to have amazing young people, including this guy again, Ali. Diversity has a huge part to play in all of this because science is global and science knows no boundaries. And so I think we've proved over the 50 years or more in 6 universities and in one company where I spent 3 years. I also have 2 startup companies, 4 countries, and during this time, roughly 50 different nationalities who get on extremely well together among 500 graduate students and postdocs. And just to put it in context, because I heard over lunch that Professor Haddadin is also a poet, and I want to share with him this piece of Scottish poetry from Robert Burns. Then let us pray that come it may, as come it will for all that sense and worth over all the earth shall have preeminence and all that, for all that and all that. It's coming yet for all that man to man the world over shall brothers be for all that. And that's a sentiment that was expressed all these years ago by a person who has more statues to him than any other human being on the planet in many, many different countries. So this type of thinking, I think, will overwhelm where we are, at least in the Western world, in a backward sort of way. This will overtake it in the fullness of time, and I think it will happen sooner rather than later, and hopefully, for the sake of the young people in the audience, very soon. Thank you.
We're going to take questions. Please raise your hand so that we pass the microphone for any questions. Let's say for 10 minutes. Any questions? Don't be shy. Here, to the front. We have a winner.
Hello, my name
Hello.
is Makhlouf. Amazing talk. Thank you so much for your time. I'd just like to ask, producing these molecules, how does it usually work? Is there a biological process to be able to synthesize them possibly? Or is it completely artificial from the bottom up?
So your question is, could they be produced biologically? You know, anything is possible. I mean, I realize that you can train microorganisms to do remarkable things just by feeding them the right components. You know, our work has all been done in a abiotic sort of chemical world, and then, you know, this could be a new track for a young person to follow, is how do you take this science and do it at the interface between biology and chemistry. You create an artificial end game, but you use all the, you know, sophisticated tricks of biology to get you there, perhaps more efficiently and more quickly. Good suggestion.
Next
Yep.
question, Muhammad. You're one of your most favorite followers.
He's a Twitter ban, isn't he?
Hello. I'm sorry, I have very brief information about the topic. I just wanted to ask, how do you think the molecular technology and thus the nanotechnology can benefit our communities and the world in general?
Ooh, that's a big question. You know, nanotechnology, I think, is already benefiting the world in many, many different ways that have made their reach into molecular or into electronics, into the IT industry, and also into medicine, of course. This particular story, I think, is the early days, and it is going to take a development period of probably decades to have the artificial molecular machines produce at the drop of a hat, in one fell swoop, whatever you want to use as a quick phrase, a new material with very, very you know, important properties, or a new way of handling disease in our human world, which of course we are all very, very interested in, and particularly as the demographic business gets to the point of people living longer and longer. So, you know, a lot of money is being invested in all sorts of areas of nanotechnology, and it's still at the forefronts of people's mind, because the American Chemical Society used nanoscience and nanotechnology as its sort of banner in Boston only 2 weeks ago.
Dr. Halawi, right here.
Thank you very much. This is really very fascinating, fundamental work and more. I have two small questions. The first, is this working?
Yes, yes.
The first is, we hear about the promise of these machines in various areas of science, sort of in future applications, and I'd like you to comment on their promise for their promise in energy storage systems or perhaps in molecular electronics? The second question is, I'm not sure how the process of discovery or the techniques that you used, where you said dynamic NMR and XRD, have you observed perhaps solvent effects? I mean, how were you able to convince that, you know, what you're observing in the XRD is what's happening in the solution?
Okay, well, I'll take your second question first. I would say, as in just more traditional molecular chemistry, a snapshot in the solid state 9 times out of 10 carries through as well as we can map out in solution by all kinds of 2D NMR methods, etc., etc. So, you know, I think we're usually in the same ballpark, you know, within little changes, whether we be in solution or whether we are in the solid state. If we then turn to the effect of solvents, they are huge. And I would admit that one of the things that we've not done is create a chemistry which we could with our systems in water. You may have noticed that we used a soft counterion, hexafluorophosphate, and this was amenable to working in polar organic solvents like principally acetonitrile. But if we switched over to working with the tetrachloride, then I think we could have a very interesting time and maybe a more efficient way. And of course, we would be in a greener sort of mode of working if we made these molecules in water. So I keep encouraging my students to take forays like that. Your other one was essentially, to begin with, just remind me, the promise, energy storage. Yeah, well, you know, tongue-in-cheek, I sometimes say, if we pack enough rings onto a chain, particularly that chain has positive charges, and the ring has positive charges, we're upping the energy all the time. Could we start to think about a molecular battery? A completely different concept? Maybe.
Dr. Arij?
Good afternoon. Thank you for an amazing talk. I'm just curious about the choice of the diaphenate warfarin to be participating as a core in such an amazing dream for the application behind.
Yeah.
Thank you.
Well, I really need to have Indra here to answer your question. He's one of these people just in the mold of Ali Trabulsi here, who goes off on his own and designs experiments. I guess he sees the porphyrin as a way of, as it were, imaging a cell. And I'm not saying that we're in the treatment situation, but more in a diagnostic realm of work in that respect. But just to concentrate on the person for a while, Indra said to me just before I left to come here, he said, "Can you give me some advice, Fraser? I can't sleep at night." And I said, "Well, what's wrong?" He said, "Well, I keep waking up and thinking of new ideas to carry out in the lab." And he said, "Should I be worried?" I said, "No, not at all. Just get up and write them down before you forget them." Yeah?
Any other questions? Okay, before we close this wonderful session, I would like to remind you that Sir Fraser will also deliver a mentoring talk tomorrow.
Can I have one hit back?
Go ahead.
So I was hoping that somebody might ask, is there more to it than just the science and the production of possibly applications? And I'm often on record as saying that my legacy will not be perhaps my scientific discoveries, but the fact that I have mentored people like Ali Trabulsi, 500 of which more than 100 have gone out into academia, probably 200 and odd out into industry. many into government laboratories, and even some into publishing and things like that. So I see myself as fulfilling the role of a professor, perhaps more than most people do in this business. It's not so much about doing research for research's sake, it's about mentoring and interacting with young people, and that's where on a daily basis I get most of my kicks. I mean, I'm very privileged to be able to go into a laboratory that we happen now to call the Research Palace, that is full of young people with great ideas and huge passion to do chemistry, and that keeps me
Perhaps
going as
you would
well.
like to share with them how many miles you flew this year?
Oh, last year it was 333,000, yes? Yeah, this year it'll be over 500,000, just to meet people like you.
He travels all over the world. So Sir Fraser will be giving a mentoring talk tomorrow at 5 p.m. in Hustler Auditorium. Sir Fraser will be talking to us tomorrow about research excellence through innovation, doing your own thing. At the end of the mentoring talk, Sir Fraser will be delighted to autograph copies of the event poster to all attendees, every one of you. We hope to see all of you tomorrow to attend another inspiring talk by Sir Fraser. Kelly Ferris will be doing some TV interviews on the way up with that. We thank you for attending, and we hope you have a great evening. Thank you.